What if everything we think we know about being Earth's first intelligent species is completely wrong? What if advanced civilizations rose and fell millions of years before humans even existed, leaving behind only whispers in the geological record that we're just now learning to decode? The evidence is hiding in plain sight. Ancient nuclear reactors that operated flawlessly for hundreds of thousands of years, extinction events that happened impossibly fast, carbon signatures in ice cores that don't match any known natural process, uranium enrichment that requires technology we only mastered decades ago, found in rocks that formed when dinosaurs ruled the Earth. Prepare to question everything you thought you knew about our planet's history, because what we're about to explore suggests that humanity might not be the first attempt at intelligence, we might be its latest survivors. Let's begin. Deep beneath the African soil, in the heart of Gabon, lies evidence of something that should not exist. Natural uranium ore had somehow arranged itself into perfect nuclear reactors, complete with control mechanisms that prevented meltdowns and waste disposal systems that contained radiation for millennia. These weren't crude experiments, they were sophisticated power plants that operated flawlessly long before the first fish developed legs. The Oklo uranium deposits reveal reactor cores where uranium-235 concentrated itself into critical masses, then moderated its own reactions using groundwater as coolant. Imagine a campfire that automatically adjusts its own fuel supply and never burns out of control. But campfires don't require advanced physics and engineering knowledge that humanity only mastered 50 years ago. Each reactor produced about 100 kilowatts of power and ran for hundreds of thousands of years before shutting down safely. The waste products remain exactly where they were left, contained in natural clay barriers that prevented contamination from spreading. Scientists studying these sites found isotope ratios that match modern nuclear waste, proving these weren't just random chemical reactions. But here's what makes this discovery truly unsettling: the precision required. Natural uranium ore contains less than 1% of the fissile uranium-235 needed for sustained nuclear reactions. But at Oklo, concentrations reach the exact 3% threshold required for criticality. The probability of this happening randomly across 17 separate reactor sites is mathematically negligible. Some researchers suggest these formations resulted from unique geological conditions that no longer exist on Earth. The ancient atmosphere contained different oxygen levels, and slower-flowing groundwater could have concentrated uranium over millions of years. But this explanation requires an extraordinary series of coincidences occurring simultaneously across multiple sites. The reactors operated during Earth's Great Oxidation Event, when cyanobacteria first pumped oxygen into the atmosphere and triggered the planet's first mass extinction. This period saw dramatic changes in ocean chemistry and atmospheric composition. Could some ancient species have developed nuclear technology as their world transformed around them? Could they have built these reactors to power underground facilities while the surface became uninhabitable? We find no artifacts, no tools, no clear signatures of intelligence. But absence of evidence becomes less meaningful when you consider the timescales involved. 2 billion years of erosion, tectonic activity, and geological recycling would erase nearly every trace of even the most advanced civilization. Metal corrodes, concrete crumbles, and organic materials vanish completely. Yet the nuclear waste remains, locked in rock formations like a message written in atoms. The isotope signatures tell a story of controlled fission, precise engineering, and contained disposal. They represent technology that humanity struggles to achieve even today. If these reactors were built by intelligence rather than accident, we face a disturbing possibility. We might not be the first species to discover nuclear power on Earth. And if we're not first, what happened to whoever came before us? The answer might be waiting in the rocks themselves, written in the language of extinct atoms and forgotten elements.
66 million years ago, a space rock ended the age of dinosaurs in minutes. But what if some dinosaurs had already built cities, developed agriculture, and started manipulating their environment before the asteroid hit? The Silurian Hypothesis suggests that advanced reptilian civilizations could have thrived for millions of years without leaving any traces we'd recognize today. Dr. Gavin Schmidt, a NASA climate scientist, proposed this thought experiment to highlight how difficult detecting ancient civilizations actually becomes. He named it after the intelligent reptiles from Doctor Who, but the science behind it is deadly serious. If an industrial civilization existed on Earth 50 million years ago, how would we find evidence of their existence? Consider the enormous advantages dinosaurs had over early mammals. Triceratops possessed brains larger than modern elephants and lived in complex social groups. Velociraptors demonstrated sophisticated pack hunting strategies that required communication and planning. Some species, like Therizinosaurus, grew to massive sizes while maintaining herbivorous diets, suggesting they had solved large-scale agricultural problems. The fossil record shows dinosaurs dominated Earth for over 160 million years. That's 800 times longer than modern humans have existed. During this vast period, countless species evolved, adapted, and developed increasingly complex behaviors. Some built elaborate nests, others traveled thousands of miles in coordinated migrations, and many displayed the kind of intelligence that could theoretically support technological development. But finding proof of dinosaur cities poses nearly impossible challenges. Fossilization requires very specific conditions that preserve only tiny fractions of ancient life. Most dinosaur fossils come from creatures that died near water and were quickly buried in sediment. Urban environments, agricultural areas, and manufacturing centers rarely provide these preservation conditions. Even more problematic is the recycling nature of Earth's geology. Tectonic plates constantly move, subducting old ocean floor into the mantle while creating new crust at spreading centers. The oldest ocean floor on Earth is only about 200 million years old. Any evidence of coastal civilizations gets systematically destroyed and recycled into molten rock.
Continental surfaces fare slightly better, but erosion, weathering, and sedimentation bury or destroy surface features over time. Mountain ranges rise and fall, rivers change course, and glaciers scrape away entire landscapes. The Appalachian Mountains were once taller than the Himalayas, but hundreds of millions of years of erosion have worn them down to gentle hills. What about technology that might survive these processes? Modern materials like plastics, refined metals, and concrete would decompose or become unrecognizable within millions of years. Even radioactive waste from nuclear power plants would decay beyond detection in the timescales we're considering. However, certain signatures might persist in the geological record. Large-scale mining operations could leave distinctive mineral distributions in rock layers. Industrial pollution might create unusual chemical concentrations in sedimentary deposits. Mass agriculture could alter soil compositions in ways that fossilize over time. The absence of these signatures doesn't prove dinosaur civilizations never existed. It might simply mean we don't know where to look or what to look for. But if dinosaurs did build technological societies, their fate offers a sobering lesson about the fragility of even the most successful civilizations. Recent discoveries have revealed that some dinosaur species were far more intelligent than previously thought. Troodon had a brain-to-body ratio comparable to modern birds and showed evidence of complex social behaviors. Some species used tools. Others appeared to practice basic agriculture by managing plant growth in specific areas. If dinosaur intelligence had continued evolving for even a fraction of their 160 million year reign, they might have developed technologies we can't even imagine. Their solutions to engineering problems could have been so different from human approaches that we wouldn't recognize their artifacts as artificial constructions. The asteroid impact that ended the dinosaurs came without warning. Even an advanced reptilian civilization would have had no time to prepare for such a catastrophic event. Their cities, their knowledge, their entire technological heritage could have been erased in the global firestorm that followed the impact.
but perhaps some survived. Deep underground facilities, protected by miles of rock and earth, might have sheltered small populations through the aftermath. These survivors could have emerged to a devastated world, forced to start over from scratch, while their former civilization became nothing more than compressed carbon in coal deposits. The coal we burn today might contain the fossilized remains of the first technological civilization on Earth.
If an entire technological civilization vanished from Earth's surface, what traces would actually survive after 100 million years? The answer is both everything and nothing, depending on where you look and what you consider evidence of intelligence. Start with the most obvious markers of human civilization. Cities, roads, and buildings would disappear first. Even our most massive concrete structures would crumble into unrecognizable rubble within several million years. Steel rusts away completely in wet climates within centuries, and aluminum corrodes more slowly, but still vanishes over geological timescales. Glass breaks down into sand, plastics decomposed into molecular fragments, and even our nuclear waste becomes undetectable as radioactive isotopes decay. But some signatures prove surprisingly persistent. Large-scale mining operations create distinctive geological features called anthropogenic deposits. Strip mining copper or coal leaves scars in rock formations that could remain visible for tens of millions of years. Underground mines collapse and fill with sediment in patterns that differ noticeably from natural cave systems. Urban heat islands represent another potential marker. Large cities raise local temperatures by several degrees compared to surrounding countryside. This warming affects local weather patterns, plant growth, and seasonal cycles in ways that influence sediment deposition. Ancient cities might leave thermal signatures embedded in rock layers like fossilized temperature readings. The most persistent evidence might come from mass extinctions. Human activity is currently driving species to extinction at rates roughly 1,000 times faster than natural background extinction rates. This creates a distinctive signature in the fossil record where diverse ecosystems suddenly collapse and never recover their original complexity. Any advanced civilization would likely cause similar ecological disruptions that persist as gaps in the fossil record. Even more subtle markers exist in carbon isotope ratios. Burning fossil fuels releases carbon with distinctive isotopic signatures that differ from carbon cycled through living organisms. Industrial civilizations would pump massive amounts of this ancient carbon into the atmosphere, creating detectable spikes in carbon dioxide levels preserved in ice cores, marine sediments, and fossil plant tissues. Consider how metal processing might leave traces. Smelting ores concentrates heavy metals like lead, mercury, and cadmium in ways that don't occur naturally. Ancient smelting sites could remain detectable as unusual metal concentrations in soil and rock layers even after the original processing facilities erode away. Earth operates like a massive recycling plant that systematically destroys every trace of surface civilizations through processes so thorough and relentless that even advanced technological societies leave almost no detectable traces after just a few million years. Understanding these geological erasure mechanisms reveals why finding evidence of ancient civilizations becomes nearly impossible over the timescales we're considering. Tectonic plate movements represent the most powerful civilization-erasing force on Earth. Continental plates drift across the planet's surface at rates of inches per year, causing collisions that crumple surface features into mountain ranges, bury entire regions under sedimentary deposits, and subduct coastal areas into the molten mantle where all evidence melts completely. Ocean floor spreading creates new crust at mid-ocean ridges while destroying old crust at subduction zones. This process completely recycles all oceanic crust within about 200 million years, meaning any evidence of ancient coastal civilizations gets systematically fed into Earth's interior and destroyed.
The oldest ocean floor on Earth is only about 200 million years old.
But here's the critical insight. We're looking for evidence of something we don't understand using methods designed to find things we already know exist. Ancient civilizations might have used technologies, materials, and energy sources completely different from our own industrial approaches. Their footprints might be hiding in plain sight, written in a language we haven't learned to read yet. Satellite archaeology demonstrates how subtle traces become visible with the right tools. Buried Roman roads show up in aerial photographs because they create slight changes in soil chemistry that affect plant growth. Ancient building foundations appear as geometric patterns in wheat fields. Archaeological sites reveal themselves through tiny variations in ground temperature detected by thermal imaging. The question isn't whether ancient civilizations left traces, it's whether we're sophisticated enough to recognize them when we find them. Deep in Antarctic ice cores, scientists found carbon isotope ratios that tell impossible stories. The numbers don't match any known natural process, yet they appear consistently across multiple drilling sites and span thousands of years. These chemical fingerprints suggest massive releases of ancient carbon into the atmosphere at times when no natural mechanism could account for such events. Carbon exists in two stable forms that act like geological fingerprints. Carbon-12 makes up most natural carbon, while carbon-13 appears in smaller but measurable amounts. Different processes create distinctive ratios between these isotopes. Plants prefer lighter carbon-12 during photosynthesis, creating predictable patterns in organic matter. Volcanic eruptions release carbon with different ratios depending on the source of the magma. But the mysterious signatures don't match either category. They show carbon isotope ratios consistent with massive fossil fuel burning occurring at irregular intervals throughout the past several 100,000 years. These spikes appear suddenly in the ice record, persist for centuries or millennia, then disappear just as abruptly. The timing makes no sense from a natural perspective. Ice ages and interglacial periods follow predictable cycles driven by Earth's orbital changes. Natural climate variations produce gradual shifts in atmospheric chemistry, not sudden massive releases of ancient carbon. Volcanic activity can inject large amounts of carbon dioxide into the atmosphere, but volcanic carbon has distinctly different isotope ratios that don't match the mysterious signatures. Ocean circulation changes can mobilize carbon stored in deep water and marine sediments. During rapid climate transitions, warming waters release dissolved carbon dioxide and methane from underwater deposits. But these natural carbon releases show characteristic isotope patterns that again don't match the anomalous readings from ice cores. Some researchers suggest the signatures result from massive forest fires or peat bog combustion during particularly dry climate periods. Burning organic matter does produce carbon dioxide with the right isotope ratios, but the scale required to create the observed atmospheric changes would need to consume entire continents' worth of vegetation simultaneously. Even more puzzling, the carbon spikes often coincide with other atmospheric anomalies. Methane concentrations spike during the same periods, but methane isotope ratios suggest industrial rather than biological sources. Trace metals like lead and copper appear in higher concentrations during these episodes, despite no known natural processes that could simultaneously mobilize both greenhouse gases and heavy metals. The geographical distribution adds another layer of mystery. Ice cores from Greenland show the same anomalous carbon signatures at the same times as cores from Antarctica. This global synchronization suggests whatever caused these events operated on a planetary scale. Natural processes that affect both poles simultaneously are limited to truly catastrophic events like massive volcanic eruptions or asteroid impacts. But neither explanation fits the chemical evidence.
Independent confirmation comes from marine sediment cores extracted from ocean floors around the world. Deep-sea drilling reveals layers with identical carbon anomalies occurring at precisely the same times as the ice core signatures.
Ocean sediments preserve different aspects of atmospheric chemistry, making it nearly impossible for analytical errors to create matching false signals across multiple types of geological records. Perhaps most disturbing, some of these carbon signature events correlate with mass extinction episodes in the fossil record. Species diversity drops significantly during periods when anomalous carbon ratios appear in ice and sediment cores. Recovery takes thousands of years, suggesting whatever caused the carbon releases also triggered ecological collapse. The patterns repeat with disturbing regularity. Every few 100,000 years, the same signatures appear: massive carbon releases, methane spikes, heavy metal contamination, and ecological collapse. It's as if something keeps triggering the same sequence of events over and over again throughout Earth's recent geological history. If these signatures represent natural processes we don't understand, they reveal something unprecedented about Earth's climate system. If they represent something else entirely, we're looking at evidence of industrial-scale activities occurring long before humans existed. Either possibility demands a complete re-examination of what we think we know about Earth's history. The ice remembers everything, and it's telling us a story we're not prepared to hear. Hidden in rocks across 6 continents, uranium isotopes tell a story that contradicts everything we know about natural radioactive decay. These atomic fingerprints appear in formations spanning millions of years, showing enrichment patterns that require sophisticated separation technology humans only developed during the atomic age. Yet the rocks containing them formed when dinosaurs ruled the Earth. Natural uranium contains 99.3% uranium-238 and less than 1% uranium-235. This ratio remains constant across the solar system because both isotopes decay at predictable rates that haven't changed in billions of years. Nuclear engineers can calculate exactly how much uranium-235 should exist in any sample based on its age and geological context. But samples from multiple mining sites contain uranium-235 concentrations that exceed theoretical limits. Some rocks show enrichment levels reaching 15 to 20%, ratios that could only result from artificial isotope separation using gas centrifuges or electromagnetic methods. Natural processes cannot concentrate uranium-235 without also concentrating uranium-238 in predictable proportions. The enriched samples don't cluster around known nuclear facilities or weapons testing sites. They appear in ancient rock formations, prehistoric riverbeds, and geological layers that predate human civilization by millions of years. Carbon dating and radiometric analysis confirm the host rocks formed during periods when complex life barely existed on land. Even stranger, the enriched uranium often appears alongside other isotopic anomalies that suggest controlled nuclear processes. Plutonium isotopes that don't occur naturally show up in trace amounts within the same rock samples. Neptunium ratios indicate artificial transmutation reactions. Fission product isotopes like cesium and strontium appear in concentrations and distributions that match nuclear reactor waste. Independent laboratories have confirmed these results using different analytical techniques. Mass spectrometry, neutron activation analysis, and gamma-ray spectroscopy all produce consistent readings. Sample contamination has been ruled out through careful chain of custody procedures and analysis of surrounding unaffected rock.
The geographical distribution spans enormous distances and diverse geological settings. Enriched uranium signatures appear in Canadian shield formations, Australian desert deposits, Siberian permafrost, and African crater sites. The common factor is not location or geological age, but rather proximity to areas with unusual mineral compositions or evidence of ancient hydrothermal activity. Some samples show clear evidence of controlled nuclear reactions that operated for extended periods. Isotope ratios indicate sustained fission processes that maintained steady power output while preventing runaway reactions. Neutron flux patterns preserved in surrounding minerals suggest reactor geometries designed to maximize fuel efficiency and minimize waste production. The reactor signatures differ substantially from the natural Oklo reactors in Africa. While Oklo shows evidence of water-moderated reactions that started and stopped based on groundwater availability, these mystery reactors appear to have used sophisticated control mechanisms. Isotope distributions suggest active fuel management, precise neutron control, and deliberate waste processing. Critics argue that unknown geological processes might concentrate uranium isotopes through selective leaching, transport, and deposition. Certain minerals preferentially absorb uranium-235 during formation under specific temperature and pressure conditions. Hydrothermal solutions might selectively dissolve and transport different uranium isotopes based on subtle chemical differences. But proposed natural explanations require multiple improbable conditions occurring simultaneously across diverse geographical locations. The statistical likelihood of natural isotope fractionation producing reactor-grade uranium concentrations at dozens of sites becomes vanishingly small when calculated rigorously. The isotope evidence points toward controlled nuclear technology operating millions of years before humans discovered radioactivity. If confirmed, these findings suggest civilizations capable of sophisticated atomic engineering thrived and vanished long before recorded history began. What's most unsettling is the implication. If ancient civilizations mastered nuclear technology, what level of advancement did they achieve? And what happened to them that left only these atomic whispers buried in stone? The fossil record reveals 5 major mass extinctions that wiped out most life on Earth. But closer examination shows some happened impossibly fast. Natural disasters like volcanic eruptions and asteroid impacts take time to spread their deadly effects around the globe. Yet certain extinction events killed species on multiple continents simultaneously, suggesting coordinated destruction that exceeds any known natural mechanism. The end Permian extinction, 250 million years ago, eliminated 96% of marine species and 70% of land animals. Traditional explanations invoke massive volcanic eruptions in Siberia that pumped greenhouse gases and toxic chemicals into the atmosphere over hundreds of thousands of years. But recent high-precision dating reveals the extinction occurred in less than 20,000 years, possibly as quickly as a few thousand years. 20,000 years sounds like a long time, but represents an eye blink in geological terms. For comparison, human industrial activity has measurably altered global climate in less than 2 centuries. A natural process that kills nearly all life on Earth in 20,000 years requires energy release rates that exceed any known geological mechanism.
The Siberian Traps volcanic province produced enormous lava flows during the end Permian period, but detailed analysis of lava chemistry reveals inconsistencies with the extinction timeline. The most massive eruptions occurred after many species had already disappeared from the fossil record. Initial volcanic activity was relatively modest and shouldn't have triggered global ecological collapse. Even more puzzling, the extinction affected different environments in coordinated waves that don't match volcanic impact patterns. Deep ocean species died first, followed by shallow marine life, then terrestrial ecosystems. Volcanic gases typically affect land environments before penetrating deep ocean waters, reversing the observed extinction sequence. Carbon isotope signatures preserved in rock layers show atmospheric carbon dioxide concentrations spiked dramatically during the extinction period. But the isotope ratios don't match volcanic carbon sources. They suggest massive releases of organic carbon from forest fires, soil decomposition, and marine ecosystem collapse, rather than direct volcanic emissions. The end Cretaceous extinction 66 million years ago shows similar anomalies. The asteroid that killed the dinosaurs certainly had enough energy to trigger global environmental collapse, but timing evidence suggests major ecosystem disruptions began before the impact.
Dinosaur diversity was already declining, marine food webs were destabilizing, and atmospheric chemistry was changing months or years before the space rock arrived. Core samples from the impact crater reveal multiple layers of shocked minerals and debris that don't match single impact predictions. Some evidence suggests a series of smaller impacts or explosions occurred before the main asteroid hit. Alternative explanations invoke massive volcanic activity in India, but again, the timing doesn't align perfectly with the extinction sequence. The end Triassic extinction 200 million years ago eliminated 76% of marine species and allowed dinosaurs to diversify and dominate terrestrial ecosystems. Proposed causes include volcanic activity, climate change, and ocean acidification, but the speed of species loss exceeds models of natural environmental change. Ocean chemistry data shows rapid acidification that killed marine organisms with calcium carbonate shells within thousands rather than millions of years. Natural carbon dioxide increases from volcanic activity typically take much longer to acidify ocean waters significantly. The observed chemical changes suggest concentrated acid release rather than gradual atmospheric carbon dioxide buildup. What emerges from this analysis is a pattern of coordinated, rapid environmental changes that consistently exceed what natural processes should be able to produce. The extinctions show signatures of deliberate environmental manipulation rather than random natural disasters. Some researchers propose that ancient civilizations might have triggered rapid environmental changes through industrial activity, warfare, or technological accidents. Nuclear weapons testing, large-scale fossil fuel burning, or failed geoengineering projects could theoretically cause extinction-level environmental damage within thousands of years. But such explanations require advanced technological civilizations existing millions of years before humans evolved. The fossil record shows no clear evidence of intelligence during these ancient periods, though absence of evidence becomes less meaningful over geological timescales. Whether natural or artificial, these extinction events demonstrate how quickly global ecosystems can collapse when pushed beyond critical thresholds. The pattern repeats itself throughout Earth's history, like a recurring nightmare written in stone and bones. The speed of death tells us something disturbing about the nature of collapse. When systems fail, they fail fast, and they fail completely.
The Drake equation predicts millions of intelligent civilizations should exist in our galaxy alone, yet after 70 years of searching, we've detected nothing but cosmic static. This absence of alien signals led to the Great Filter Hypothesis, one of the most disturbing ideas in modern science. It suggests something destroys nearly all intelligent life before it can spread beyond its home planet. The numbers should be encouraging. Our galaxy contains roughly 400 billion stars, and recent discoveries show that most stars have planetary systems. Conservative estimates suggest billions of planets exist within habitable zones where liquid water can exist on their surfaces. Even if intelligent life is extraordinarily rare, the sheer number of opportunities should produce detectable civilizations somewhere in our cosmic neighborhood. But the electromagnetic spectrum remains eerily quiet. Radio telescopes scan millions of frequency channels across thousands of star systems without finding artificial signals. Optical searches look for laser pulses or megastructure signatures that would indicate advanced engineering projects. Infrared surveys hunt for waste heat from massive energy consumption that any expanding civilization would produce. The paradox becomes more puzzling when considered against the backdrop of cosmic time. Stars have been forming planets for over 10 billion years, giving evolution enormous time spans to produce intelligence. Even if intelligent species appear rarely, older civilizations should have had billions of years to develop technology that reshapes entire solar systems in detectable ways. This paradox led Robin Hanson to propose the Great Filter concept in 1996. Somewhere between the formation of planets and the emergence of galaxy-spanning civilizations, something acts as an evolutionary bottleneck that eliminates almost all potential intelligent species.
The filter could operate at any stage of development, from the origin of life itself to advanced technological phases. Early filter scenarios suggest life itself is extraordinarily unlikely. Despite billions of years and countless planets, perhaps Earth represents the only location where self-replicating chemistry successfully emerged from non-living matter. The transition from simple organic molecules to living cells might require such precise conditions that it rarely occurs, even given geological timescales.
Alternatively, the filter might eliminate species during the transition from simple to complex life. Earth took over 2 billion years to evolve nucleated cells from bacterial ancestors. This enormous time gap suggests the development of cellular complexity faces fundamental barriers that most biospheres never overcome successfully. Intelligence itself might represent the filter. Despite millions of species evolving on Earth over hundreds of millions of years, only one lineage developed technology capable of spaceflight and radio communication. The cognitive abilities required for science and engineering might emerge so rarely that most planets with complex life never produce tool-using intelligence. But late filter scenarios offer more terrifying possibilities. Perhaps intelligence regularly evolves throughout the galaxy, but technological civilizations systematically destroy themselves before achieving interstellar expansion capabilities. Nuclear warfare, ecological collapse, artificial intelligence disasters, or other technological catastrophes might represent nearly insurmountable challenges for developing species. The timing of humanity's emergence adds urgency to these considerations. We developed agriculture, writing, and industrial technology within the past few thousand years after millions of years of hunter-gatherer existence. This rapid technological acceleration suggests we might be approaching our own encounter with whatever filter eliminates most intelligent species. Current human activities show potentially fatal patterns. Climate change threatens global agricultural systems. Nuclear weapons proliferation increases risks of civilization-ending warfare. Artificial intelligence development proceeds rapidly with insufficient safety research. Ecological destruction eliminates species at rates comparable to previous mass extinctions. If the Great Filter lies ahead of us rather than behind us, humanity faces challenges that have defeated countless previous civilizations. The silence from space might represent not the absence of intelligence, but rather the graveyard of species that failed to navigate the transition to sustainable interstellar existence. Frank Drake's famous equation promised to calculate the number of communicating civilizations in our galaxy, but 70 years of searching has revealed a terrifying mathematical reality. When we plug realistic values into the Drake equation, we discover that intelligent life might be so extraordinarily rare that we could be alone not just in our galaxy, but the entire observable universe. Conservative calculations suggest fewer than one technological civilization per galaxy exists at any given time. More pessimistic estimates indicate civilizations might be separated by millions of galaxies and billions of years. The Fermi paradox crystallizes this mathematical nightmare. If intelligent life should be common, where is everybody? The absence of alien signals becomes not a mystery requiring explanation, but rather the expected result of universal mathematical realities. Our survival might depend on recognizing and successfully passing through whatever evolutionary bottleneck has eliminated our potential cosmic neighbors. The Great Silence isn't just the absence of alien voices, it's the echo of countless civilizations that tried to speak but never learned how to survive long enough to be heard.
4 billion years ago, Mars had flowing rivers, vast oceans, and an atmosphere thick enough to support liquid water on its surface for millions of years. Recent discoveries reveal this ancient Mars might have been more hospitable to life than early Earth, raising profound questions about what kinds of organisms or even civilizations might have thrived there before the planet died. The evidence comes from multiple Mars rovers and orbital surveys that have mapped the planet's geological history in unprecedented detail. Ancient riverbeds snake across the Martian surface for thousands of miles, carved by water flows that persisted for millions of years. Sedimentary rock layers show clear evidence of lakes and shallow seas that existed during Mars's warm, wet period. Spectroscopic analysis reveals clay minerals that only form in the presence of liquid water over extended periods. These clay deposits contain complex organic molecules and chemical signatures consistent with biological processes. Some formations show layered structures similar to stromatolites on Earth, which represent some of our planet's earliest evidence of microbial life. But Mars had advantages over early Earth for supporting advanced life forms. The planet's smaller size meant lower gravity that would have made flight easier for any evolving creatures. Reduced atmospheric pressure would have allowed more efficient gas exchange for respiratory systems. The planet's distance from the sun provided protection from solar flares and radiation that bombarded inner planets. Most intriguingly, Mars appears to have maintained stable climate conditions for much longer than early Earth. While our planet experienced several snowball Earth episodes and massive volcanic catastrophes, Mars enjoyed relatively gentle climate variations during its habitable period. This stability might have given evolution more time to produce complex organisms and potentially intelligence. The planet's two small moons, Phobos and Deimos, create unique tidal patterns that differ dramatically from Earth's single large moon. These complex tidal cycles might have provided additional energy sources for early life and created diverse ecological niches that could support rapid evolution toward intelligence. Recent discoveries of subsurface water, ice, and possible liquid water reservoirs suggest Mars might have remained partially habitable even after surface conditions deteriorated. Underground ecosystems could have provided refuge for organisms as the planet's atmosphere gradually escaped to space. Advanced species might have developed subterranean civilizations to survive the changing surface environment. The timing of Mars's decline coincides with several dramatic events in the inner solar system. Asteroid bombardment increased significantly around 3.8 billion years ago during a period called the Late Heavy Bombardment. Multiple impacts could have stripped away Mars's atmosphere while simultaneously delivering water and organic compounds that jump-started life. Some impact craters on Mars show unusual characteristics that don't match typical asteroid collisions. Circular formations with raised rims and central peaks appear in clusters that suggest coordinated impacts rather than random bombardment. Alternative explanations invoke volcanic activity or tectonic processes, but the crater patterns don't match these natural mechanisms either. The loss of Mars's magnetic field remains poorly understood. Planetary magnetic fields require molten metallic cores with active circulation patterns. Mars apparently lost its magnetic field quite suddenly around 4 billion years ago, leaving the planet vulnerable to solar wind erosion that gradually stripped away its atmosphere. But magnetic field loss doesn't necessarily happen quickly through natural processes. Earth's magnetic field has reversed multiple times throughout geological history without causing permanent atmospheric loss. The rapid disappearance of Mars's magnetic protection suggests either catastrophic core cooling or external interference that disrupted the planet's internal dynamics. Before Venus became a hellscape hot enough to melt lead, it might have been the most beautiful planet in the solar system. For nearly 2 billion years, Venus likely had oceans, moderate temperatures, and atmospheric conditions that could have supported not just life, but potentially advanced civilizations that thrived in a paradise we can barely imagine. Computer climate models reveal that ancient Venus probably maintained liquid water oceans until as recently as 700 million years ago.
During this period, the planet received about 70% more solar energy than Earth, but a thicker atmosphere and global cloud cover could have reflected enough sunlight to maintain temperatures suitable for life. The planet's extremely slow rotation, taking 243 Earth days to complete one turn, would have created unique weather patterns unlike anything on Earth. Massive atmospheric circulation cells would have transferred heat from the day side to the night side, preventing extreme temperature differences. This could have created vast temperate zones where liquid water remains stable for millions of years. Recent atmospheric analysis by space probes has detected phosphine gas in Venus's upper atmosphere. On Earth, phosphine is primarily produced by biological processes, though some geological sources exist. The concentrations detected on Venus exceed what known non-biological processes could produce, suggesting possible microbial life still surviving in the planet's acid clouds. But the phosphine discovery raises intriguing questions about Venus's biological history. If simple microbes can survive in the planet's current harsh upper atmosphere, what kinds of life might have flourished when Venus had oceans and moderate surface temperatures? Advanced ecosystems could have evolved during the planet's billions of years of habitability. The transformation from paradise to hell happened relatively quickly in geological terms. Runaway greenhouse warming triggered by volcanic outgassing gradually increased surface temperatures until the oceans boiled away completely. This process would have taken thousands or millions of years to complete, potentially giving any existing civilizations time to recognize the threat and develop countermeasures. If Mars once hosted intelligent life and Venus supported advanced ecosystems for billions of years, then our solar system might have been home to multiple civilizations that rose and fell long before Earth developed complex life. The red planet and the morning star could be archaeological sites, preserving evidence of intelligence that predates humanity by billions of years. We're not just alone in space, we might be latecomers to a cosmic graveyard. 7 miles down in the deepest ocean trenches where sunlight has never penetrated and pressure would crush submarines like tin cans, strange geometric formations appear on sonar maps that don't match any known geologic process. These underwater features, hidden beneath miles of water and sediment, might preserve evidence of civilizations that thrived when the ocean floor was dry land millions of years ago. The Mariana Trench, Earth's deepest point, plunges over 36,000 feet below sea level into a world more alien than the surface of Mars. Recent deep-sea mapping reveals rectangular formations, perfectly straight lines, and circular structures arranged in patterns that resemble urban planning more than natural geology. These features span miles in diameter and show geometric precision that defies explanation through conventional geologic processes. Tectonic activity constantly recycles ocean floor, making it impossible for surface features to survive more than 200 million years. But some deep ocean formations appear much older based on sediment analysis and magnetic signatures. Layers of accumulated debris bury these ancient structures under thousands of feet of mud, creating time capsules that preserve whatever existed before the current ocean floor formed.